So, welcome to Module 3, Structure 3. So in Structures 3, we have a topic, the 3moment theorem. Or what we refer to as the theorems. The theorems theorem. So this theorem is used to analyze continuous beams, and only 3 supports are considered at a given time. Take a case of a beam. Continuous beam, the support A, C, B, and support C, like so. Let support AB have moment of inertia 1 and at its length 1. Span BC, moment of inertia 2, length 2. Assume that is carrying a UDL load. Of 32 kilonewtons per meter. Let's so. So when this beam is loaded, it buckles or it sags, giving a deflected shape, like so. That one, like so. So let point B act as a pivot so that A and C are free ends. Therefore, support A will be displaced downwards. Let me use different color. So if we draw a tangent touching the deflected shape of the beam, like so, passing through point B, these points, like so. Call this one Z1 and call this one Z2, like so. Therefore, this one will be A prime and this is C prime, like so. Therefore, this tangent makes an angle theta with a horizontal axis, like so. So, for us, we have first to sketch the BMD. Call this one area 1 and this one area 2, like so. For this one, this distance x1 and that distance x2. This is the BMD, bending moment diagram of a simply supported beam. That's a continuous beam with the simple supports at the end. For a beam with fixed ends, at point C, like so. So you can divide this one So, yeah. So that this is moment A, this is a moment at B, and this is a moment at C, like so. This is length 1, this is length 2. Therefore, this one will act, should not be this way. Should be the other way. It should be that way. So, for this one, to left a third of L1, and that of L2, this is 2/3 of L2, this is 2/3 of L1. This was area 1, area 2, call this one area 3, area 4, this is area 5, and this is area 6. For the centroid of this one, we lacked a point, that point there. This one will be a point there. Remember, this is a triangle. This one will be a point there. And this one will be a point somewhere there. So that the centroid is a third of the total length AB, like so. From there, we remember the Moley's second theorem that states that the moles, maybe I can write it here, Moley's second theorem states that for a beam, that was initially straight, the vertical displacement of 1 point in relative to the tangent from the second point is equal to the first moment of area of the BMD measured from where displacement is required divided by EI. Like so. And therefore, let's come to this point. This angle theta, so we say tan theta will be given by Z1 over L1. The distance from here to here is L1. So it is Z1 over L1, which is equals to Z2 here over L2, which So this one, equation 1, like so. So following Moley's second theorem, we get that Z1 equals 1 over EI1, open the bracket, area 1 multiplied by x1. Remember, we have said that is equal to the first moment of area of the BMD. So it is the area multiplied by the distance to where displacement is required. The vertical displacement where the vertical displacement is required, plus area 3 multiplied by a third of L plus area 4 multiplied by 2/3 L1, like so. So this one will be our area 3, this one will be given by a half moments at A multiplied by L1. And then you multiply by a third of L. Plus, it should be L1, like so. Then you add area 4 here, which will be given by a half. We multiply by moments at B. You multiply by L1, then you multiply by 2/3 of L1, like so. And then from there, we get that plus this one, we get moments at A, L1 squared, because this is L1 squared, all over 6, plus this one will be 2 moments at B, L1 squared, all over 6, like so. Factoring 6 outside and then dividing by I will give us 1 over 6E this one should be 6 area 1 x1 all over I1 plus moments at A else L1 squared all over I1 plus 2 moments at B L1 squared all over I1, like so. Remember, our tan theta equals Z1 over L1, so we divide all through by L1. So this one will give us 1 over 6E area 1 x1 all over I1 L1 plus moments at A. This one will be L1 all over I1. Remember, dividing by L1 cancels with one of the L1 and we are left with L1 plus 2MB L1 over I 1, like so. And this is our equation 2, like so. So from there, we come to this one. Will be given by, this is Z2 equals 1 over EI2. Remember this, our I2, we open the bracket, area 2 multiplied by X2 you add area 5 multiplied by 2/3 of L2 plus area 6 multiplied by 1/3 of L2. Like so. So this one will give us and so this one should be negative because this one should be tan inverse. Therefore, it should be negative. Therefore, negative 1 over E I2 in the bracket here 2 X2 plus our area 5, this one will be given by half multiplied by MB and by L2. So a half multiplied by MB multiplied by L2 and then you multiply by 2/3 of L2 then you add half the area 6, so it is a half multiplied by moments at C multiplied by L2, you multiply by moments at C, no sorry, moments at C multiplied by L2 and then you multiply by 1/3 of L2. Like so. This one will give us negative 1 over EI 2 area 2 X2 plus this one will be 2 moments at B multiplied by L2 squared all over 6 plus this is moment at C L2 squared all over 6, like so. We factor out 6 and then we divide all through by I2, so this one will be negative 1 over 6E in the bracket area 2 X2 should be 6 area 2 X2 divided by I2 what 2 moments at B in the 2 squared all over I2 you add moment at C, L2 squared over I2. Like so. From there, from equation 1, tan theta equals Z2 over L2. So we divided everything by L2. So this one will give us 1 over 6A, 6 area 2, x2, all over I2, L2, like so, plus 2MB, L2, all over I2. Remember now it is not squared because it has been divided by length 2. You add moments at C, L2 all over I2, like so. And this is our equation 3. Remember this is our Z2. But from our equation 1, Z1, our Z1 here, it was our Z2 here. Therefore, we can put the two equations. Yeah. So, it should be negative, so negative. Or maybe you can start with this one. So this is 1 over 6A. 6 area 1, x1, all over I1, length 1, plus moments at A, L1, all over I1, plus 2 moments at B, L1, all over I1, this one equals to this one, so negative 1 over 60 in the bracket, this 6 area 2 x2 all over I2 L2 plus 2 moments at B length 2 all over I2 plus moments at C L2 all over I2, like so. So you can multiply this one by 6e and this side by 6e, and therefore this one will cancel out, these ones will cancel out, like so. Therefore, we can put, from there we can put the moments together from to one side and the areas to one side. Therefore, we put the moments at this side, so there's this moments at A, I1 over I1 plus 2 moments at B divided by length 1 over I1. We have these moments. Remember, we are taking this one, this one, this one, and this one, like so. So this is, remember it has a negative here, so when it comes to this side, it becomes a positive. So these are 2 LB, L2 over I2 plus moments at C, L2 all over I2. This one equals 2. Remember, this one is also, this is positive, gives us negative. When it comes to the other side, it becomes positive. On the other side, this one is positive. When it comes to the other side, it gives us negative. Therefore, negative 6. Area 1, x1, all over I1, all over I1 and L1. This is negative 2. Therefore, it will be negative 6. Area 2, x2, all over I2, L2. Like so. So, this one will be moments at A, L1, all over I1, plus this one can factor out 2 moments at B, this is L1 over I1 plus L2 over I2, like so. Then you add moments at C, L2 all over I2 equals 2. This one we can factor out to negative 6. And the bracket is area 1, x1 all over I1, L1, put a positive, area 2, x2 all over I2, L2, like so. And this is our 3-moment equation. This formula will enable you to calculate the moments for continuous beams. Thank you for watching. Don't forget to subscribe. Thank you.